It's disabled for us.
Yeah, now it's okay, right? I have started. Okay, good. So we would significantly discuss about this syntax directed translation and how Bison can actually generate such a translator with actions written by us. So this is going to be a very core. I mean, we are kind of at the middle of the course, and we are kind of about to discuss the most crucial tool in the whole course before we move on from next week on in terms of the actual translation actions. So let me first get back to where we left in the last class in terms of the LR parsing. So we had been talking about SLR parsing. Let me go back a few slides. So after having talked about LR0 parsing, where we made the state machines based on collections of LR0 items, which mark up to which point in a production rule you have actually seen, and what you expect to see in future. We saw that there are certain grammars which are LR0, where there are states containing single complete item, where we know that once you have reached that state, you just all that you need to do is to just do a reduction. You already have got the handle and you need to do a reduction by that production rule. Replace it by the left hand side non-terminal and take appropriate transition in the state machine again and proceed to find the next handle. And that works for some grammars. And then we came across grammars like the one you are seeing right now, where in a single state we have a complete as well as incomplete item. And most importantly, this tells us that because of the incomplete item where a dot is before a terminal symbol, so we have an action of shift to take in that state, here state 2. And also there's a complete item S produces A dot where we should actually reduce. So in the same state, we have two possible actions and we get to a situation of shift reduce conflict. On this, we argued that, while this can happen in a LR0 parser, it is not difficult to resolve that because we can see that after the reduction, when the right hand side is replaced by the left hand side non-terminal, then the symbol in the look ahead that was existing must belong to the follow of the left hand side non-terminal. Because if it does not belong to the follow, that is, if this symbol can never occur right after this non-terminal in any derivation, then certainly this reduction would not have been possible. So based on that, in the earlier grammar, we saw that the follow of S, the left hand side non-terminal when S produces A dot is dollar, and so we can say that when in this state I have A in the input, my input symbol is A. Naturally, I cannot do a reduction because if I did a reduction, that would bring me to a sentential form where A will be right after S, which is not what is possible because of the follow information. So we can, resolve the conflict between shift and reduce here and decide to shift. Similarly, in this case, in state 3, we have a shift reduce conflict on plus, and we can resolve that in terms of, we can know that E cannot have plus in its follow, it has dollar. It cannot have plus in its follow, and you can say that this will also get resolved in terms of doing a shift action, which is what we mentioned here. So this is the actual parser that you get. You had a conflict here in state 3 on input symbol plus, and you resolve that in favor of doing a shift, not doing the reduce, because reduce would have meant that after reduction, plus will be to the right of E, which is not possible according to if you compute the follow in of E here, which is very clearly just the dollar symbol. So shift reduce conflict of this in LR0 parser can be resolved by using the following information, and that leads to a class of parsers which we say are SLR or simple LR parser. So this is another example which you are supposed to practice. The solution is given in the next page. Now we move on to see that will SLR solve, will work for even bigger grammars, and we stumble immediately on a grammar which is very typical of an assignment statement that you would like to write, assignment expression that you would like to write for a programming language. And we find that in state 2 here, we have again a shift reduce conflict. Now here it says that I should shift on the assignment symbol, and it says that I have to reduce. So I compute the follow information. So if I compute the follow, S produces L assignment R, and L produces star R. So I see a derivation of this sentential form here where equal to symbol occurs to the right of R, and therefore I can say that equal to belongs to the follow of R. So now you can see that even SLR will fail because I cannot decide based on this follow information of equal to that, I will shift or I will reduce, because doing a shift also would be fine here. Doing a reduce would also be fine here. So I cannot resolve that. And then I have to actually think deeper to understand that, well, it is true that the equal to can come to the right of R at this point, but in reality, this equal to cannot come to the right immediately to the right of R if the production R produces L is used in the derivation process. Just look at this. In this derivation process, R producing L has not been used, right? I have got the equal to immediately to the right of R, saying that it is in the follow, true, but it cannot be in that position if R produces L were used in this production. You'll have to try out with this grammar a little bit and get convinced that if you use R produces L in the derivation, then you will not be able to get the equal to symbol to the right of this. Right? So it says that it is not enough only to just look at the follow. It is important also to know the left context as to how did you get there. So SLR misses out on that left context. If you do LR0, then it does not have any left or right context. So it is only on the state. If you do SLR, you are just trying to look at the immediately right context of the sentential form, but you have no left context of how you have reached that sentential form. So in grammar like this, that also fails. So what you do is what you move on to as LR1 parser. What you do is something very, very simple. That why do you want to look at the follow? You exactly want to know that if I'm at a situation where I've got the handle, where I've done a replacement exactly at that, replacement in the derivation, that is my left-hand side of the non-terminal is replaced by the right-hand side, so that in the reverse, I will do a reduction. At that point, I exactly want to know what are the symbols that can occur to the right of the non-terminal. So I free myself of the generic definition that SLR was using, that I will have a follow, which means that this particular terminal will occur to the right of this non-terminal in some sentential form. No. Now I say that I would exactly keep on doing the construction of the sentential forms and keeping track of what all symbols can come right after a non-terminal. And that is called the look-ahead computation. So what I do is very simple. There's a grammar, the augmentation. So I extend the LR0 item into LR1 item, which has a LR0 part and a look-ahead symbol. So it says that if I have seen for the production A producing alpha beta, which I've said alpha dot beta, it says that I have already seen alpha part of it because the dot is here. And I expect to see whatever comes from beta. And after that, after what I've seen, whatever is from beta, I expect to see a terminal A. I will always compute that. Now, how do I keep computing on this? So this is what is called a LR1 item. So LR0 item plus the look ahead symbol. So when this beta eventually turns out to be epsilon, so I reach a complete item, A produces alpha dot. I still have this A, small a terminal after this, which is a look ahead symbol. So I know exactly that when I'm going to do this reduction, then what is the look ahead symbol that I'll have? Now it is quite obvious to understand at this point that if A produces alpha dot, comma A is an LR1 item, then small a belongs to the follow of capital A, the non-terminal symbol. Because certainly after this reduction, this small a will be to the right of it. But it does not mean that everything that may exist in the follow of A will occur as a look ahead symbol here. So I have very specificity of what can be looked ahead at. So here are some of the LR1 items coming from, say, production 1, production 2, or production 3. So naturally, when I start the whole thing, my starting is at here where S produces dot CC and dollar, because dollar is the starting point, which is the end of the string input mark. Now, naturally, the question of how do I get to the closure, that is, how do I expand after this dot? It is quite obvious that if I have the dot coming before a non-terminal symbol, say A produces alpha dot B beta T, if I've got this in the derivation, then naturally B produces gamma. Any production rule from B will generate a LR0 item, B produces dot gamma. Now the question is, what will be the look ahead symbol? Obviously, the look ahead symbol would be what can get generated from beta. Whatever can get generated from beta. So whatever that can start with can be the look ahead symbol right after the non-terminal B. What is that? That is the first of B, first of beta. So first of beta could be here, but first of beta could also be epsilon. That is, this could generate nothing, an empty string. Then obviously the look ahead symbol would be T. So I can put this together and say that what can be there in the look ahead is the first of beta T. I will take beta T string, compute the first, and whatever symbols it has, it could be 1, 2 more. Obviously one symbol will have to be there. Then for all of them, from this B goes to dot gamma LR0 item, I'll have those many LR1 items. That's precisely what is happening here. And here is a closure examples given, and naturally canonical collection of LR1 items will give me LR1 states. So these are again like LR0 construction, but I have very specifically the look ahead information for every LR1 item. So this is for this grammar, we do this few steps. I will just walk through with you. The rest you can certainly take care. So this is the augmented grammar. So this is our first LR1 item, S primed, the extended augmented production, goes to dot S comma dollar, which is the obvious look ahead. Now, if I do closure of that, I get the 3 productions with dot at the beginning. And I will have their look ahead as dot S is going. So it is the look ahead is the first of beta is empty here, beta dollar. So it is dollar. So I get dollar. Then I have this dot precedes C. So these 2 productions come in. So what is the look ahead? The look ahead would be first of the second C and dollar. Now what is the first of C? First of C is obviously small c or small d. So first of small C dollar will be either small c or small d. So naturally I have 2 items here which I write as C or D. Similarly, I have 2 items here which I write as C or D. This is as simple as that. It's just as straightforward. So then I have a transition on S, which is quite obvious. There's nothing. Yes, I have a transition on capital C. So as I do capital C, I get this item. Then I have got a closure. Now we can see that the look ahead is different because I'm doing a look ahead, which is the first of beta, which is empty dollar. So I'm doing a look ahead, which is of dollar. So I get look ahead dollar. I get on small c, I come to I3. So this dot moves to C dot. I have the look ahead, which is epsilon union C or D. So I get C or D, which is obvious look ahead. Similarly on D, I get similar transition. On this, I do C, I'll get the same thing. On this, I get D, I will come here. These are very simple things. On this, I have capital C, I'll have a complete item, CC dot. And now I have here, I can see that beta was epsilon. So I have a look ahead, which is C or D. So I can see that clearly now I'm saying that in state 8, I have a complete item C produces CC dot, and in state 8, the look ahead has to be C or D. Similarly, in I4, I have a complete item C produces D dot, look ahead has to be C or D. But if you follow the transition from I2 on this D, you'll get to I7, which is also a complete item. But there C produces D dot, so I will reduce on this production a complete item. But my look ahead is dollar. So you can see that between I4 and I7, in both I will reduce by C producing D, but my look ahead would be different. Similar things happen between I9 and I8 as well. If you go through this, again, I will reduce by this production C produces CC, but here I will do it if the look ahead is dollar. Here I will do it if the look ahead is C or D. So you can think of that if I was doing an SLR construction, I would have got all of them in the same state, and I would have said that whatever is there, irrespective of that state, whatever is there in the follow, where all of these would be in the follow, obviously, because they're in the look ahead, would be eligible for reduction, and thereby I will get shift reduce conflict. Similar thing happens here. Now you code this into the table, and this is what you have got. So you can see, for example, if you see in state 4, on C and D, you have this reduction, R3, reduction by R3, this one. In state 8, you have reduction by R2 on C or D. In state 9, you have reduction by R2, but on dollar. Similarly, on I7, state 7, you have reduction by R3, C produces D, but on dollar. So you will have, please mute yourself. Please mute yourself. Okay, thank you. So this is what gives you the state machine. So you'll see that if you try to construct an SLR parser for this grammar, you'll have shift reduce conflict, but maintaining the look ahead symbol, we can very straightforward construct in a similar way an LR parser. So this is called an LR1 parser because it is LR, and at every point you are making a one symbol look ahead. So this is the most powerful parser construction algorithm that we will follow in this course. That's a customary one. You don't typically do LR2 or others. And if you use Bison parser generator, then you are actually constructing LR1 parser. Right. So this is the parser. This is another example. So this one is where we did an SLR earlier. We can do LR1 for this as well. You can construct that and see how that works out. Now, just before I conclude, I would like to mention that, well, there's something that you can, certainly what will happen is, as you can see here, certainly the sets of LR0 items are the same. If you had just done a LR0 construction, you would have got this state, you would have got this state, you would have got I3 and I6 would have been the same state, I4 and I7 would have been the same state, I8 and I9 would have been the same state, I1, I5 would have been there. So instead of having 10 states, you would have got 7 states, because I8 and I4 would have been same, I9 and I7 would have been same, and I6 and I3 would have been same. But they would have had shift reduce conflict, because you would not have computed the look ahead. You would have just computed the follow. Right? So what it means, I mean, this is a small example, but what it goes to show that as you do LR1, coming from LR0 SLR construction, as you do LR1, you get a lot of proliferation of states. Your size of your state machine immediately starts becoming much, much, much larger. I mean, in reality, it is quadratically larger compared to your LR0 state machine. Potentially, I mean, it can happen. Not that for every grammar that will happen. So, which means that this state machine is this state transition table. So that has thousands of states now. And obviously, if you have that, then you have a very large state machine to load in memory while you are actually executing. And we will have those many more state transitions to happen. So exploding in terms of the number of states which is required to compute the look ahead symbol is, on one side, making a state machine which has a state transition table which is too large often, and might find it difficult to fit in memory. So it's a runtime resource issue. And at the same time, since there are more states, there are more transitions happening. So it slows down the performance of the parser as well. So on one side, this was required to compute the look ahead symbol in a more fine way than just doing the follow. But in that process, it actually explodes in terms of the performance. So there is a very quick, trick that we would normally do on an LR1 parser is which is called the LA LR1 parser, look ahead LR1 parser. I mean, just for the search of a name. I mean, look ahead, of course, was there, but it's a search of a name. It's called a look ahead LR parser. So what it does, it computes the LR1 states as it is. That's no difference. But then it collapses states where it has the same set of LR0 items. So we talked about state 3 and state 6. They have the same LR0 set of items. So it collapses them into one state, say state 3, 6, because LR0 items are same. And then you take a union of the look ahead symbol. So this had C or D, this had dollar. So you make that into an item C or D or dollar. Similarly, you get the second item, you get the third item. Similarly, you can merge state 4 and 7. So you do like that. So as you do that, then you get something like this. So you had 10 states. Now you have merged 3 and 6 into 1, calling the state 3, 6, 4 and 7 into 1, calling the state 4, 7, 8 and 9 into 1, calling the state as 8, 9. So if you look into this table above, this is the LR0 table and the LR1 table, and below is the LALR1 table where you have collapsed the states. Then if you look at 3, 6, so that you're taking the row of 3 and the row of 6 and putting them together. So there's no conflict. They were 3, 6. When you collapse, this was going after, it was doing shift and going to state 3, this was doing shift and going to state 6. In each case, it now goes to state 3, 6, which is the merge state. Similarly, here it was going to state 4, and on 6, it was going to state 7. After merge, it goes to state 4, 7. You can with a little bit of thinking, you'll be able to convince yourself that by doing this merging, you will never have a shift conflict. You will never have a conflict that you need to shift to inconsistent states. Similarly, if you merge 4 and 7, 4, you are doing reduction to R3 by C and D, which you have here. And on 7, you are doing reduction to 7, which is in R3. You can have this. So you can see that after this collapsing, you have reduced from 10 states to 7 states, which is again exactly the same number of states that your LR0 machine would have had. But The LR0 machine coupled with the follow information could not give you a SLR1 parser, but now having done LR1 and got back to LALR1, you have been able to get a machine which is of exactly the same size as the LR0 machine, but has adequate look ahead information to solve. So it's kind of a win-win situation. You have solved, you are being able to resolve for bigger grammars using the look ahead information, but you are building a parser which has exactly the same size of the states. So it will have exactly the same size for the state transition table and as well as for the actual number of transitions that you do at the runtime. So LLR1 often, so if you use Yak, you normally, if you use Yak, the earlier version of the Bison generator, then you generate a LLR1 parser. So your question would still be that, well, if that is the case, if it is so hunky-dory, then why does Bison generate LR1? So without going into much ado about specific programming language issues, I've just presented here an example of a grammar. This is a grammar which is it's not a meaningful grammar in terms of the programming language constructs, but just use this grammar to see on the left the LR1 parser construction. It has a LR1 parser, no conflict of shift reduce. You can have a bottom up LR1 parser for this grammar. Now, when you do conversion to LLR1, then there are two states whose LR0 items are same. So they are identical LR0 states which are different in terms of the look ahead. And when you merge them, you'll find that you get a state like this where A produces C dot earlier was getting reduced in this state by D and in this state by E. But now it gets reduced by D or E. Similarly, in this state, B producing C was getting reduced for look ahead E. Here it was getting look ahead T. Now, when you put them together, they have now conflict because on D, you do not know which production you will reduce by. We are getting a different kind of conflict, not a shift reduce one. But on the same input symbol, on the same look ahead, there are two productions available in the same state which are ready for reduction. You do not know which one is the hand. So in this case, we say we have a reduce conflict. So what happens when you collapse LR1 parser into an LLR1 parser, you might potentially get reduce conflict. And therefore, there may be grammars like this one, which has a LLR1 parser, but which has a LR1 parser, but may not have a LLR1 parser. So to take care of that, Bison typically does a LR1 parser, but then it will try to optimize into LALR1 if one is possible. So that's kind of the in very short nutshell the LR parsing theory. Let me pause for a little bit, and then before I go on to discuss the actual Bison generator. Let me check if there is any question. We are not looking into the theory, as we know. We just showed the construction process by example. Yeah.
There are no questions on the chat. Someone was asking, I don't know whether there can be shift or reduce conflict, which you have already answered.
Shift conflict can never happen. Actually, that is because it cannot happen because you do shift on a single terminal. So in LR0 construction, it is not possible. When you are merging states in LR1 to get LLR1, at that it is not possible because you are merging based on the same LR0 items. So on same LR0 items, you are certainly, if there is a terminal after the dot, then they have to be identical between the LR0 items because the LR0 items are same between the two states. So there cannot be a shift conflict. There is only a shift reduce conflict that happens in LR0 for going to SLR1 and then you go to LR1. Or when you merge, there could be the reduce conflict, whose example I have shown. Okay, so let's move on to more. I'm sorry. More useful stuff for us on engineering wise more useful. This was kind of the glimpse of the algorithm which built this and kinds of the background of the theory, which I could not do in full. But let me move on to the parser generator, the Bison. So naturally, the objective is clear. We want to have a generator which will generate a LR parser. So let me move on to the specification of this. And in this, Bison starts fitting in here. Lexical analyzer is generated by Flex, we have seen. So Bison generates a syntax analyzer, and inside the Bison, we will put enough action rules to actually start doing the syntax analysis. So we'll see how things go. So let me, I think I'll start with an example first, and then come back to talk about the different parts of this. So this is a simple expression grammar. So the first thing I'm trying to do is to write a parser. So this will, given the grammar, will give me a parser so that when I input a valid string, it will parse and tell me it is valid. And if I give it a wrong string, it will tell me it is wrong. That's the only thing we are looking at. So here's the expression grammar. There's no identifier here. Everything is a constant, comes from num. Otherwise, it has plus, minus, star, divide, parenthesis, and unary minus. So it's a little extended form of an arithmetic expression grammar having only constants, operators, and parentheses. Right? Now, this is the simple flex. So it has numbers. So number is, we for simplicity, we are excluding 0, only 0 here. So this starts from 1 onwards. And in that regular definition, it returns number, which is a manifest constant token, telling us that we have got a number. And here we ignore the white space, which is space and tab. We ignore them. We don't ignore new line as a white space, which is customary as you start working with the parser, because you often need the new line to be counted specifically, recognized specifically, because without the new line, you would not be able to trace the line number. And without the line number, you will not be able to give the error messages when you need to give them. So new line is normally not clubbed with a white space. It is considered a useful symbol. So you have this. Dollar is a terminating symbol for your input stream. So on dollar, you return 0, indicating that you are done. And on any other symbol, which will be, what will be the other symbols available in this grammar? Other symbols will be, we have already taken care of this. Other symbols will be plus, minus is operator symbols and parentheses. So on all of them, you just return YY text 0, which means you return the symbol itself. Because these are, everything else will be a single lexem token. And so it is what you will find in the YY text 0. So for this dot, you return that. Otherwise, you have a new line, so you return that new line. So this is the simple thing that your flex will do. Only catch is you have a include here, which is y.tab.h, and you do not have a hash defined for number. The reason for this is y.tab.h gets generated by Bison, and as we'll see, the Bison, there's a little bit of handshaking for meta symbols that happen between flex and Bison, so that when Bison generates this header file, it generates a manifest constant for number, so that I don't need to really do that. We'll see that in detail. Don't worry about it. But this flex specification, I'm sure you understand very well. It comes in 3 parts. It does not have anything in the third part, because you don't expect to have a main routine, because you are going to use this lexicon analyzer not by itself, but along with your Bison generated parser. And as you can easily see from this return and all, that this is being designed in an interactive mode. Now this is the Bison specification. Here's the grammar for your easy reference. It again has 3 sections. separated by percentage, 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 percentage. First part is a definition part, which again has a first C declaration and definition part, which is like, I mean, all headers and C functions that you need for the parser. Then it has a definition part of the parser itself, where you're saying that number, as we have seen here, number here is a token. So you're saying that number is a token. You'll say, okay, there are more tokens like plus. If I come back here, plus is a token, minus is a token, star is a token. So kind of you're saying that, well, if it is a single character token, is a single lexem token like this, then you don't really give it a name. You may not give it a name. But if it is a multi-character token, like 135, then you call it a token number. Okay? So percentage token is a specific keyword in Bison, which says that number written anywhere is a token. And this is also the clue which will tell Bison that number needs to be generated as a manifest constant, because your flex will use this number and return you this number value as a token. Right? So that's the percentage token. Then in the second rule section, you write the production rules. You can see how you are writing it. Colon is a separator between the left hand side and the right hand side. So left hand side is always a single symbol. You can give any names to the symbols. Like I've got S as statement. I've written expression for E. And you can write the rules here. After the colon, you keep on writing the right hand side. Alternates of the rule are shown by vertical bar. So there are 3 rules from E here. So you do not write it thrice. You could, but you can write them together. Expression, colon produces expression, plus this is a single symbol token. I just put it within single quote. Term. I'm writing term for T. Or expression minus term, the second rule, or just a term. And this sequence you end by putting a semicolon. So semicolon says that whatever your left hand side was expanding into has ended. So this says that there are 3 rules here. Whereas this says that there are 1 rule from starting from the statement non-terminal. Similarly, there are 3 rules from T star F, T slash F, F. So these are written here. Term star factor, F is factor, term slash factor, factor, semicolon. There are 3 rules from F, which is F produces opening parenthesis, E closing parenthesis, opening parenthesis, expression, closing parenthesis. Again, single character tokens directly put here. Then minus F factor or number. So this is where you are making use of the fact that token is a number. Yeah, number is a token. So you are putting number for num and semicolon. So this is your collection of all different rules. So these are your production rules. Right? Then you have some auxiliary. This YY error, which you have forward declared here, is a function that in which you can write your actions if there is an error. So it's saying that if the parser gets into an error, if it cannot parse the string, then the Bison generated parser will call this YY error function. So whatever you write here, and to the YY error, you can pass a string. So that's a signature that you can see here. So here, for example, I've just done that. It's called on error, so it just prints. Please try to mute yourself, please. And finally, you have the main driver. So as your lexical analysis, flex specification, when you compile it by flex, it generates the whole flex driver as YY-lex, as we have seen. Similarly, Bison generates the whole parser as YY-parse. So YY-parse is a function that Bison will generate by itself. So it will get generated somewhere. You don't need to forward declare that. So your job is just to call that parser. And that parser assumes that your associated flex parser, flex analyzer is the function YY-lex. So you're doing an extern of that here. So that's a simple specification, goes very intuitively straightforward, I think. And that's how your parser gets ready. So these are the notes associated with it. Number is identified by percentage token. Single character tokens are specified directly in the rule. We will see, we have not done this yet. We will see that non-terminals may also be specified by percentage type. Well, how do you know what is a non-terminal? Anything that occurs on the left-hand side is a non-terminal. So statement, expression, term, factor. They have occurred on the left-hand side, so they are non-terminals. So wherever they occur on the right-hand side, they are non-terminals. Everything else is either single character token, so they are terminals, or they are defined to be token number. There's nothing else you can do. Right? So non-terminals are easy to detect in this way. But you could also say percentage type expression here to explicitly tell the parser that you have a non-terminal expression. We will see why we need that. Well, so that's the percentage type. Production rules start with a non-terminal on left, separated is colon. Multiple right-hand sides are separated by alternate rule. A series of rules ends with semicolon. So that's all we have discussed. Okay, what is the first production rule? The first production rule is the one that is written first. The production rule that you write first is the first production rule. But you have the option. So productions from statement is a first production rule. But you have an option to define that start symbol by doing a percentage start. You can do say percentage start and say percentage start statement, which will mean that production starting with statement is the beginning of the derivation process. So these are the simple Bison rules. So okay, so this is the parser, which is quite intuitively obvious, I think. Okay, should I break for once and just check in case you are having some doubts? You should not, but still. Anything, students?
So can you explain why we include YY tab? I got disconnected. Why in text language YY tab.h.
I will not explain right now, Tanmay. You're Tanmay, right?
So
So I will not explain right now. I have, a couple of slides down, I have an illustration which will explain that. Okay. So I have an illustrative example which will show you why you include y.tab.h and what it is. Okay. Anything else? So let me continue and complete this. Okay. So let me move on to, we just did a simple expression parser. Let me elevate this to a calculator. So for the same grammar, I want to do a calculator, which means that if I give an expression, earlier I was expecting my Bison generated parser to just say yes or no. Yes, that okay, this is a valid expression. No, saying that this is an erroneous expression. No, I do not want that. Now I want that if I give an expression, if it is valid, it will parse and also evaluate that expression. So if I say 12 plus $8, then it will actually evaluate and give me 20. So that's how it's. So it's like this is like a typical calculator, right? This is you have a plus b, a minus b, a star b, like that. So minus a parenthesis. So this is like a typical calculator. So if I write any expression involving constants and this, then I want to write a program which is a parser or semantic translator parser cum semantic translator generated by Bison, which will evaluate that expression after parsing. Right? That's just the beginning of this is the first example you are seeing of how translation actually can get automated. Okay, this is the Bison specification. On the top, there is no difference. These are forward C declarations. On the bottom, third section, there is no difference. All the driver and the error function. Now, in terms of the Bison declarations, you have token, but along with that, you also have declarations for different non-terminals. Of that statement, we have not given a percentage type. We'll see why. It's not required. You could have given. But expression, term, and factor, we have said that they are percentage type this. Now you're saying that, okay, the question you'll ask us to why am I doing this? Why do I need this? Because in any case, it was obvious from the specification of the parts, of Bison, that what are the non-terminals. Why do I really need to say type along with it, percentage type along? Okay, the reason is arising from the fact that I'm now no more happy to just parse. I want to evaluate. So I'm saying that look at the grammar again, go back and look at the grammar again. Every non-terminal symbol here in the grammar actually stands for a value. Num is a terminal symbol which stands for a value. 123, 358, 12, 17. These are different possible values of num. But then as I go on this, every factor has a value. So if f produces num and num is 12, then the value of f after reduction is 12. If f is 12, then by this production, what you mean is by reduction, if f is 12, then this f has a value which is minus 12. If this e is 3, then by this reduction, this f is 3 as well. If here in production rule 5, t is 20 and f is 4, then by this reduction, this is 20 times 4, this t is 80. Okay? So all that he is saying is the fact that every non-terminal has a value. And that is the value that I finally compute. That is the value of the expression that I finally compute. So if every non-terminal has a value, I need a placeholder. I need a variable. I need a location. I need a position in the stack to remember that value. So this is what I'm trying to do. I'm saying that I have an int val. Forget about this union stuff right now. Just think it does not exist, let's say. So as I'm saying that I have an int val type of integer variable which can store the value of an expression. Now, of course, it cannot be one variable. Then it can store value for one expression only. So all that I'm saying is okay. Let me think of it in this way, that this int val, for every expression, I can have an int val variable. For each instance of an expression, I have an int val variable. So if whatever my expression is, that int val variable corresponding to that expression non-terminal has the value of that expression. Similarly, I have an int val variable available for every instance of the term. So if I say here, then there's an int val for this term, there's an int val for this factor. And when I do this multiplication in the parse tree, then these two int vals get multiplied 20 times 4, giving me 80, which is the int val value of the term t on the left-hand side. So all of these, we are saying that each one of these non-terminal must get associated in every instance with an integer variable, where I can keep the value of that non-terminal. So that's the important factor in terms of saying that this percentage type. So percentage type is not only telling me that this is a non-terminal. That's one part of the information. It's also telling me what is the kind of type of variable or the name of the variable that I can associate with it to keep its value. And herein I'm saying what is the type of that variable. Similarly, in percentage token, I have also elevated. Earlier, I had written percentage token number. Now I'm again writing percentage token within corner braces int vals, which says that the number also has a value on the stack. Whenever the number comes, it will come with a value which will be in a associated int val named integer variable. So that's what it is trying to say. Okay, now let's see how do we use it. Okay, now what is say? So now we are saying that every production rule is just not the rule, but it is associated with value. Every symbol is associated with value. So how do we designate the values here in general? So what he is saying that in a production rule, start on the right-hand side and start counting symbols. The first symbol on the right-hand side has a value which is called $1. Second symbol on the right-hand side has a value which is called $2. Third has a value which is called marked by $3. In this way, you keep on doing that. And the value associated with the left-hand side non-terminal is called $. Now, mind you, it is not necessary that in a production rule, all of the symbols must have a value. So obviously, if a symbol has a value, then for that, I need to have either a percentage token or a percentage type declaration above to tell me what is the name of that variable and what is the type of that variable which holds that value. Otherwise, it is just a placeholder and I will not be able to write the corresponding dollar as a value. So you can see here, I have $1 here meaning expression. I have $3 here meaning term. I have $2 here meaning the value of plus, which has no value because I have no token defined as plus here associating it with a variable of value. So I cannot use $2 and I don't need to. Why don't I have it? Because I don't need to. Plus has no value as such. But what I have in terms of this production rule, which is what I write and I say is the semantics of this syntax of addition, is a fact that $, the value of the expression on the left-hand side, is the sum of the value of the expression on the right-hand side and the term on the right-hand side. So $, is nothing but $1 plus $3. What is $1? $1 is this expression on the right-hand side. So it is the int val, variable value corresponding to this expression here, which is $1. So it is an integer value. Term is associated with an int val variable at this instance, which is also an integer value as $3. So we take the values from these two variables, add them, and put them to, again, the int val variable corresponding to the expression on the left-hand side. And that is what completes the semantics of addition. So all that we are doing here, if you can see, is we are just defining those semantic terms that what is expression minus term in the rule is $, assigned $1 subtracted, $3 subtracted from $1, which is what it means. This is a semantic action. Similarly, the term of multiplication here, term of division has to take care of the fact that factor, the value, current value of factor is not 0. So that is $3. So we say if $3 is 0, then I have an error. So you can see how YY error is. So error gives a message divide by 0, and at this point, this function will be called and the whole process will terminate. Otherwise, if $3 is not 0, it is dividing $1 by $3 and putting it to $1. It's an integer division and an integer value. Similar thing happens for expression within parentheses because the value does not change. So whatever is the value of expression, which is $1 here, $2 here, $3 here. So expression is $2. So whatever is the value of the expression is the value of the factor. So you copy $2 to $. If it is minus, then it is minus $2 is $. Naturally, some rules are left out where the semantic action is not written. For example, you'll ask that what happens to getting the number which you are getting from the flex. So here you get the value of that number as an integer value, which is $1. That has to get copied to $. Similarly, when term produces factor, $1 has to get copied to. So whatever is the value of factor is the value of term. So $1 gets copied to $. So these are called kind of default actions. So unless if you have $1 copied to $, which is what you have here, factor producing term, number, term producing factor, or expression producing term in these cases where you have this default action, then writing this action is optional. If you do not write that action, then the Bison will always assume that $$ gets $1. It will just propagate that value. So that is what this specification is saying. So you can very easily see that it's not only the grammatical syntactic rule of expressions that we have defined, but now we have defined how to compute the expression. And finally, when I come to statement producing expression, the very fast production rule. So what will this mean? This will mean the last in the chain of reductions to happen, because it's the first production rule, it's the augmented production rule. So when this happens, then expression, which is $1, in its corresponding integer variable will have the value that has been computed out into that expression. So in this, you just print that value. So you say equal to $1, which will print the value of that whole expression. So if I wrote 12 plus $8, this will print equal to 12. So that's how my calculator gets ready. So here in, I mean, all that I have discussed is just written out. So I'm not reading it out again. Now you can see that from this specification of the Bison parser, when you do the Bison, compile it, a y.tab.h file will get generated. This y.tab.h file generates the number. This is a token, right? This is a token which the Flex needs to know. So it generates it as a manifest constant, hash defined number 258. So Flex in turn will include this y.tab.h. So it will know that number is a manifest constant. So Flex can now return number, which will return 258. You can see that it actually, Bison now actually defines this both as manifest constant as well as enum, depending on the style of programming that you want to do. You can use any one of them. They're defined to be of identical value. The value is typically 258 onwards because you do not want to clutter the area of the ASCII values 0 to 256, because single character tokens are being returned as the token itself. So plus is being returned as a token. So single character tokens will always have value between 0 to 256. So you do not want to clutter that in your manifest constant. So you put your manifest constants beyond that. So this is what you have here. Then you have your int val, and that you have put within a union. So let me just go back and talk about this union. So we say this is union. Why are you saying this is union? We said there's a placeholder for a value, because here in this example, all non-terminals needed a value which is an integer. But in general, that may not be true. In general, a non-terminal may need an associated value which could be integer. Another could need a value. For example, next we will introduce identifiers. And the moment we have identifiers, we may need to have a pointer to the symbol table entry of that identifier as the placeholder for that identifier, right? Because identifier is just a placeholder. It's not a value by itself. So it is possible that the non-terminals will have varied type of different types of values. They may not all be of the same type. So I can give a different type and name to each of these, and then I can bundle them all together into one entity by calling them as union. So it's kind of a, it's kind of taking care of multiplicity of type in a C style. You do not, this inherently could have been done by, specialization in a type hierarchy and so on, because different non-terminal symbols will require values of different types. But this is solved in a very simple, elegant C manner by saying that, okay, you put different fields as your value types in a union. The particular field that your non-terminal wants to use, associate it with the percentage type or percentage token, and then put all of these fields in a union so that for any symbol, any non-terminal symbol, you will have only one of them available. That's the beauty of the union, right? And which one would be available? You know the non-terminal, so you know which one is available. So there's no ambiguity that can happen. So that is a very elegant C solution for taking care of multiple types within one jacket. So that is, if you look into y.tab.h, so that is a union that is getting generated here, since we have used only one type of value here. So this union has only one type of field, which is int val. Rest of it is some, C preprocessor directives to control the compilation and so on. Don't worry about that. So this is the y.tab.h that gets generated from Bison and will remain included in the flex specification, so that you don't have to synchronize that flex calls number as 325, whereas Bison expects number as 129. No, you will have this. Bison has defined this, and you are including that very file in your flex specification. So you will always remain in sync in terms of what the manifest constants or enums are to exchange the different tokens. So this describes what I just said. So given that your corresponding flex specification will have y.tab.h, of course, here this is where you're getting the Bison generated symbols. Earlier, when we were just doing the parser, we just returned number. Now we have to return the value of that number because we are doing evaluation. So I need this. Going back, I need this int value to be set. Right in here, the $1 value to come here. So I need to get that value from here. So a way to return that is you return it as YYLVal. What is YYLVal? YYLVal is, I'm back to y.tab.h. This is your union. Type def union YYS type. YY prefix comes from yak convention. All yak symbols are written as YY. That's why you have YY parse, YY legs. And in capital, they are C preprocessor symbols of yak. So YYS type is YY stack type. This will go in the stack. So this is a YY stack type. So you're saying the type def union YY stack type. So this type is YY stack type, which has interval. Then you're saying extern YYS type YYLVal. So you're saying that YYLVal is a variable of type this union type. This is what it means, right? And it is defined somewhere in the Bison source. Right? So YYLVal is an instance of that union object. So it's an union object. So int val is a component of that. So YYLVal.intval is that component of the union which you want to populate at this point, because why are you populating this one? This is synced with the Bison specification here. Percentage token intval number. So number will be associated with this intval variable in the union. So you are populating it here. YYLVal.intval. And what will you populate it with? The number has found out the number string in YY text, as we have already seen. So you will do it ASCII to integer conversion. So you have got 1, 3, 7, sequence of 3 characters. Now we'll convert that into 137, and that is what you put is integer value. And then you return this number. So you can see that actually you are returning a doublet as a token. The actual return, which is the interactive part of the flex, has a value which tells you that this is number. So which will actually get you here in the parser, because you have returned a number, you've got a number here. And then this reduction will happen. And the other part of the token, which is the value of the token, is coming through YYLVal.intval, which is what is set as $1 here. Because you know the number associates with intval. So you know whatever is the value of YYLVal, the intval component of that, because number uses intval, is your $1, is your value here. And that's what gets copied to the $, and the whole process starts. So that is how the Lex very seamlessly integrates its token value into Bison. Rest of the actions are same. They are not different from what we had earlier. So this is what is described in the text here, in the notes here. And this is your final build process. On top, you already had the Lex build process. Now you can see that you have the Bison specification, which you Bison here. You'll have y.tab.h header, which is included in your lex.yy.c because you have included it in mylex.l as I have shown. And Bison will also generate y.tab.c. So lex.yy.c and y.tab.c will have to be compiled together along with the Flex and Bison library to give you the final generated syntax directed translator parser, which will take your input and give your output. So that's the whole flow process gets over. So 12 plus 8, you run, it will give you 20. You do this, looks a little complicated, this gives you 150. Okay, so I have a stack explanation of how this is happening. Before I go to that explanation, let me at this stage ask if there are any questions. Yes, please.
Okay, no questions.
Okay, good. So let me complete the discussion with the actual execution of this. Is it visible as you?
Yes, it is visible. Yes, it is visible.
So let me just show you what happens when you do a parsing of this kind in this generator, 12 plus $8. So these are the production rules. These are the actions that we have written in the Bison. I've just reproduced for your easy reference. This is the parse tree, 12 plus $8. So dollar I have not shown here explicitly. It will come to the right on top. Otherwise, you have 3 terminals here, 12, which is num, which is a num token, value 12, a plus and num. So that will have to get reduced to F1, then F1 to a T1, T1 to E2. Here, this will get reduced to F2, then to T2, then E2 plus T2 to E1. Yes. So this is the order in which things will go. So this is how it goes from here. The bottom up parsing sequence, rightmost derivation in reverse order. So what happens is I represent this. We know that when this happens, that there is a stack of symbols. Now, coupled with that stack of symbols, which is on the left, I have a stack of associated value. I've said that every symbol may have a value. So some terminals like num has a value. Some non-terminals like E, T, F have values. Others do not have values. If it has a value, then there is an associated value stack which will maintain that value. So what happens first? There's a shift of num12. The stack, it goes in num. So in the stack, symbol stack, num goes in, and the value is 12, which has been returned from flex. So that goes in. Then I have this reduction. So this comes out and replaced by F. And what happens? F produces num. So $1 gets $. So $1 is 12. That gets copied to $, which is the value of F. So this 12 comes out and the 12 of F goes in. Then I have a reduction of F going to T, that is 7, which is again $1 goes to $. So F taken out, T goes in, 12 taken out, again as $, it goes in. T is reduced to E. Rule 4, again the same thing happens. So we come to this point, E plus, E, up to E. Then the plus goes in the stack, does not have a value. So the value stack part of it is undefined. Then it gets num. So num goes in, value is 8. Then the num has a reduction to F. So $1 replaced by dollar gets 8. F gets reduced to T, dollar gets 8. So we are at E plus T, and we can see in the associated value stack we have 12 and 8. Now this gets reduced. So E plus T is taken out. This is $1 now. Look at rule 2. E is $1, which has a value 12. T is $3, which has a value 8. So these are taken out. And I do $1 plus $3, which is 12 plus 8, which is 20. So dollar is 20. So this is taken out, reduced to E. E goes in, and E goes in along with the value $, which is 8 plus 12, 20, that goes in. And finally, I have reduction by 1, wherein this comes out, this is $1 comes out. So $1 is 20. And with this production, the printf happens, which is equal to 20. So that's precisely what is going on. So it goes in sync with the stack algorithm. So that's the whole process of Bison driven translator. Next, I have an example of a programmable calculator, which I will not work through here. All that we do here are extending this from rule 4 down to rule 13. These rules are same as the calculator. I have introduced the possibility of having an identifier as an expression and an assignment to the identifier. So there is no identifier declaration. If you assign a value to an identifier, like you assign A, assigned 8 plus 9, then A is an identifier. That's it. And then wherever you use A, this value will have to be. And so this is what gives me an assignment to an identifier. And then I have in 1 and 2, I have a left recursive specification for a sequence of statements. So L produces LS, L produces S, which means that a list of statement is nothing but statements, one after the other, separated by new line. So you can write multiple of them, and then you get keep on getting the value. Now, naturally, since I have an identifier, I need a symbol table. So that symbol table will maintain the name of the identifier and the then value of the identifier. So that's all that is required. So in the Bison specification, you have the same things going on, except that now you have a symbol table that you need for the identifiers. And so you can either have reference to a value if it is a constant or an expression which is already evaluated, or if it is a symbol, then you have a reference to the symbol table. So in your union, you have two fields now. One is int val as before, and one is a pointer to a symbol table entry. So that's a pointer union of these two. So your expressions, term, factor, they all remain to be int val because they are evaluated. Number has a value which is int val, but name, which is an identifier, has a pointer to the symbol table. So this is, you can see now that if the flex returns an identifier, then it will return a pointer to the symbol table where its value will actually go. Rest of it would be very similar. Evaluation of expression, term, factor, there's no difference except that in factor you now have a name wherein you have $1 is your symbol table entry. It's a pointer to SymTab. So in the SymTab, you expect a value field to exist where the value of the identifier at this point of time would be maintained. Okay? So that's but this symbol table is required because you also need to maintain the lexem of the identifier. Otherwise, when A gets defined here and subsequently used here, you will not be able to bind these two together, because when you get this A, the only way to know that it is this A which was assigned earlier is by the name or by the lexem A, which you will have to search in the symbol table. So symbol table, besides value, will also have lexem and other fields. But those details are not important for us right now. So this is how your Bison specification goes. This is the symbol table sample code you can check out. This is y.tab.h. Now you have two token symbols, as you can see, in place of just having one number. and you have two fields for the YYS type, stack type, as in here. You have a parser header, which is a symbol table header. You have the flex specification, where you now have the identifier, and you have an identifier rule, where if it is a number, you still do yyl_val.int_val because it's a value that you return. Whereas if it is a name identifier, then you do yyl_val.symbol, where you look up the symbol table with the lexem YY text and check if it exists. If it exists, you get the same record pointer returned. Otherwise, you create a new record, put the lexem, and return that. So that's the basic process. So symbol table and details are given. Just go through that. And with that, you get convinced that if I have A assigned 8 plus 9 and A plus 4, then I'll eventually print 21. Go through these and get convinced about those. And I've shown how it works on the stack so that you can get a better idea. I'll leave that onto you to work out. Before I close, I would like to just close with mentioning that long ago, we discarded the ambiguous grammars as not workable because ambiguous grammars lead to ambiguity. So let us get back and see what happens with ambiguity if I bring it back. I mean, we discarded them in LL parsing, in the top-down recursive descent parsing. They have multiple parse trees, so they are not usable. But ambiguous grammars have a lot of advantages compared to the unambiguous grammar. So the green and red tell you that. So unambiguous grammar has uniqueness and so on, associativity, precedents are resolved. So those are difficulties in ambiguous grammar. But they have a lot of advantages. They have a smaller parse tree. They do not have single productions like this. T produces F or E produces T. So they're much smaller size, intuitive, and so on. So let's see what happens again if you try to go back and use ambiguous grammar. So I use the ambiguous grammar for example, the same expression grammar. E produces E plus E, addition, multiplication, parenthesis, ID. And here is my LR state machine. In my LR state machine, look at state 7. So what do I have? I have dot here and dot at the end. So I have a complete item. Certainly, the follow of E has plus, follow of E has star, follow of E has closing parenthesis, follow of E has dollar. It's quite obvious from here. So I can see that if I do this, then I will have in state 7, I'll have a shift reduce conflict on plus between this shift and reduction by rule 1. Similarly, in star also between this shift and reduction by rule 1. I'll have similar conflict with rule 2 in state 8. So these are the by plus I should shift to 4. I should shift to 4 over here. But by the fact that plus is in the follow of E, I should reduce by rule 2. So I have 2 states and 2 inputs where all shift reduce conflicts exist. But in this, let us refer back to the very first process we started with, is infix to postfix conversion, operator precedence. They said, okay, we know the operator precedences. We know that if I have a plus completed here and have a plus occurring here, then plus is left associative. So this plus has to happen first, which means between this shift and reduce, if I reduce, I give the left plus a higher associativity. If I shift, I give the right plus a higher associativity. So if I reduce, I have left associative operator. If I shift, I have a right associative operator. That's a simple thing to resolve. So I can resolve that very easily. Operator precedence rules. So if I make use of that, given that the plus is left associative, I will reduce in favor of, I'll decide in favor of reduce. Similarly, star is left associative. Here, star is left associative. So I'll resolve in favor of reduce again. Then between star and plus, I know star has a higher precedence than plus. So in state 8, between these two items, I must reduce first because this has a higher precedence than the incoming plus. So shift is not the way to go. It is plus. It is the reduce. So I can do a reduce. And only in the other case, in state 7, if I have a star, then plus has a lower precedence and star is in the input. So plus has to wait for the start to happen. So I'll shift. So in all 4 cases, by using simple operator precedence information, I can actually resolve the conflict and get a conflict-free grammar. So what if I use the ambiguous grammar, which is simple to write, and give these rules of precedence and associativity, then I should be able to generate a parser. And that's precisely what is done. So where this is the parser for the unambiguous grammar, this is the corresponding parser of the ambiguous grammar. It's smaller. The larger the grammar gets, this compactness of the table also increases. So if you go to Bison, you can express this. You can use ambiguous grammar exactly in the same way. You don't need to do so many of different symbols and all that. You'll get shift reduce conflict. To resolve that, you write down what is the precedence and associativity. So precedence from top to down is lower to higher. Lower down you write is a higher precedence, and you say a percentage left to say it is left associative. This is left associative. This is you're saying is non-associative. Unary minus is non-associative. So say it's unary minus token precedence here. It says is the highest precedence. Then you have the division multiplication. Then you have plus minus, which is the lowest precedence. So this is the operator precedence information we had just been using in here to decide whether to shift or to reduce. So your operator precedence algorithm embedded into the LR1 parser will use this and be able to generate a parser for this ambiguous grammar, which is simpler, which is shorter, and which, if you finally look into, if you look into the parsing, you'll see that it, compared to this, which is unambiguous grammar, to parse this sentence, these are the steps, long steps that are going on. Your ambiguous grammar, which is here, which will have a much shorter sequence of reduction. You can just compare. This is your ambiguous whole grammar doing this in a much shorter form. So this is so it is actually, we'll see that in LR parsing, we will often not only whole of it to generate our parser and write our actions, but we'll often use ambiguous grammars also, particularly for the operator part of the language. We'll often might write an ambiguous grammar and use those. Of course, it depends on the compiler writer as to how you want to write the actions often. Though it is possible to write ambiguous grammar, not always compiler writer might want to write ambiguous grammar because might want to maintain some different types of information along with the symbols. But that's the overall gamut in which you could use Bison and generate a parser. So that's what I wanted to discuss. Let me stop and ask if there are questions.
Just one thing, BPD.
Yes.
You can tell them that today the next lab assignment will be announced.
Yes. So the next assignment in the lab, assignment 4, is on Bison parser. That's right, Aish? Yes.
Yes.
So now we have just covered Bison. So for the same tiny C language for which you have done a flex, now using that flex, you'll have to also write a parser. The grammar rules are being provided. So later in the day, that assignment will be uploaded. Any questions, or everybody has gone to sleep by this long discourse?
Not sure. The sleeping or listening.
Hello, sir.
Yes, please.
Sir, when we are evaluating expression using
Uh-huh.
Bison, so if like if
See,
I
see,
use,
see, I'll correct your statement a little bit. We are not evaluating using Bison. We are using Bison to generate a translator which evaluates the expression. Bison is the generator, right? Are you getting me?
so can you repeat?
Bison is writing the specification, and then that specification is compiled to generate a translator, which is parsing and doing the evaluation.
So in actual compiler, so that evaluation thing goes by the Bison. So Bison does the evaluating in the actual compiler, like
Bison does not. Bison is the generator. Bison is the generator. You are Aryaman, right?
yes, sir.
Just look at this diagram again. See, this is where your Bison is. This is where your specification is. This is your flex. This is your flex specification. This is your Bison. This is your Bison specification. These are two compilers: flex compiler, Bison compiler. This is your C programs, and all these together gives you the a.out, which is your translator. This actually is evaluating the input into the output. So in a real situation also, this whole thing, this a.out will become your tiny C compiler, which will take a tiny C program. I'm sorry, which will take a tiny C program and will translate that into something else, into the x86. Are you getting me? So it's not proper to say that the Bison is doing the evaluation. The Bison is a specification from which you are getting your translator generated. Are you getting it, Aryaman?
Yes, yes, sir.
Okay, so that's the basic difference. So if Flex Bison were not there, what you would have required to do? You would have required to write these C programs. LR1 parser, you have to write
Yes, sir.
all these parts table from the grammar. You'll have to write by hand, right? That is what used to happen in the late 70s and 80s. But now you have generators, so you are just writing the specification, which is a very small one, and you are saying that along with every rule in the parser, in the grammar, this is the translation rule that I have. So your evaluation is a translation rule, which is saying 12 plus 8 will be 20. And that program is getting generated here, which gives you the a.out, which is actually your translator. That is the basic process. Got it?
Okay, sir.
Sir, actually, next week we have lot of assignments and tests. Could you please make the deadline a bit later? Not next week, like next to next week. For the lab.
ISG sat, please note. ISG sat, are you there?
Yes, I am there, but the lab deadline is already 2 weeks, I believe. The
So
deadline
it is
is
not
from-
next, it's not next week. It is next to next week anyway.
yes.
Okay, sir. Thank you, sir.
That is, I think, 8th of October or something, if I'm not wrong, the date.
Yeah, because this, this is relatively bigger in terms of the assignment compared to the earlier 3 that you did, and the next one would be even bigger, of course. কি করছিস?
Okay, because there are no
Anything
more-
else?
So fine then, I believe.
Okay then. Then I think we'll close here. And
Sir, please could you inform them once about that we have shifted all the assignments to CSE Moodle. Just assignment 3 has been
okay,
released
okay.
theory.
Oh. Assignment 3 of theory.
Yes.
Assignment 3 of theory has been released on CSE Moodle. Please note.
CSE Moodle. Yeah.
And assignment 4 of lab will also be released on CSE Moodle. So now, from now on, we are working with the CSE Moodle. Please take a note of that. Right, so you'll find your assignments there, and you will also submit in that. Okay. Okay, so let's just close here. I think Shoman, you have already uploaded the presentation, right?
Yes, sir.
Okay. So please, the later part in the presentation, I have just skipped slides and done that. So please go through. And if you have doubts, you ask me later on. From Monday, we will start on the new module, which will be on translation. So intermediate code translation, and translation to intermediate code is the core of the meat of the compiler is what we'll get into. Have a nice weekend, and thank you all very much. Bye.